Hello everyone, and welcome to another video on anemometry. This one we're going to discuss the cup anemometer and some of the characteristics of cup anemometers. Cup anemometers, well, the cups, they determine the response of the anemometer, of course, and also its spin up and spin down. The conical cups are preferred. They found that they have a more linear relationship. In other words, as the wind speed increases, the cups start to spin faster proportionally. And also they found that the conical cups tend to spin at lower speeds, also have lower thresholds. So conical cups are preferred over hemispherical cups. Hemispherical cups, though, you will still see on some anemometers. The 3-cup design is a good design. It's probably the most common that you see. Studies have shown that it's the best. It produces the most uniform torque than other configurations. But you'll also see 4, perhaps 6-cup designs where you have, of course, more uniform torque because there's more cups. However, adding cups adds weights, so that means that you're going to have a higher threshold speed, wind speeds, and also longer distance constants. And of course, the more cups you add, the more expensive it gets. As far as the characteristics of the cup anemometer, the arm radius typically is about 1.5 times more than the cup diameter. Also threshold speeds on the order of 1 to 2 meters per second, and then distance constants anywhere from a little bit below 1 meter to somewhere above 6 meters, but definitely less than 10 meters. So of course we talked about distance constants and threshold wind speeds before. We said that it all depends upon, of course, the inertia of the wheel. Also, it depends upon the bearing friction, and as you have bigger and bigger cup wheels, you add more mass to the assembly, and of course mass is one of the big factors in determining the distance constant. Small anemometers typically have very small arm radii and also cup diameters. And as a result, since they have less mass, the threshold wind speeds are going to be much lower, on the order of tenths of meters per second. But when you look at large anemometers, of course, they're bigger, they have more massive, so they have higher threshold wind speeds and higher distance constants. The National Weather Service standard for many years was the Belfort 2000, and that was the cup anemometer. It had conical cups. It was on the ASOS machines since 1996, since they implemented ASOS machines, and it was used by the National Weather Service before that at their weather stations. The dynamic range was from between 0 to 125 knots. Above that, they were unreliable, and of course hurricanes are stronger than that, so frequently you would see ASOS stations going offline, and they wouldn't be reporting, of course, wind speeds. Accuracy for the Belfort 2000 was plus or minus 2 knots or 5%, and the resolution was down to 1 knot. The types of transducers that are used for cup anemometers are either an AC or DC alternator / generator, magnetic and mechanical relays, or photochopper or optical transducers. So let's take a look at the first one, the AC and DC generators, the signals. So an AC or DC electrical signal is generated by the cup anemometer through its shaft. The shaft is attached to the cup wheel. The cup wheel is rotating. At the end of that shaft, there's a magnet. The magnet is rotating through an electric field, which generates a current. And that's what we can measure. We can measure the current. It could be done either AC or DC. DC would strictly be magnets. AC would be an electromagnet that's generated using an alternator, similar to an alternator. So I think you're familiar with generators and alternators, and this is more or less the electric signal that's generated. So of course, the faster the cup wheel rotates, the greater the current. If it's an AC transducer, then the voltage that's produced, its amplitude and its frequency will be proportional, of course, to the shaft rotation. But if it's strictly DC, then the voltage is proportional to the rotation rate. The problem with this type of transducer, of course, is that you have magnets at the end of the shaft. Magnets are more massive. You have more mass to rotate. So, of course, you have larger time constants or distance constants, higher threshold speeds, and, of course, this is a little bit more expensive. However, this is a very reliable technology, so they tend to survive out in the elements. Magnetic or mechanical relays as a transducer. This is where you have a magnet attached to the shaft. As the shaft rotates, there is a device, whether it be a Hall type device or something else, that actually measures the rotation or as the magnet passes by. And because of that, you can count the number of rotations of the cup over some given period of time. In other words, revolutions per minute. And based on that, you can calibrate the revolutions per minute to a wind speed. Now, once again, you have either a magnet or some sort of device attached to the shaft, so it's more massive. More massive means that you have larger distance constants, higher threshold wind speeds, but these are less expensive and they are more reliable. And this is one looks like in a cup anemometer that we have in the lab here at UND. You can see that there's a wheel that is perforated, and then there's a sensor that's measuring or can tell when it's going through a region that's either metal or non-metal, and it can count that and determine from that the wind speed. The third type of transducer is a photo chopper or optical transducer, and this is where you have a light emitting diode that is shining through a slotted cup or a slotted cylinder, and the cylinder is attached to the shaft. As the shaft rotates, those slots are rotating around with the cylinder, and if you emit a light emitting diode point that light emitting diode at the rotating cylinder, then eventually what happens is you'll see that the slots will line up and allow the light to pass through at certain times, and other times it'll be blocked. So based on the number of times that it gets a hit of light over a period of time, it can figure out the rotation rate, and from that it can figure out the wind speed. So the advantages of this is that typically this slotted cylinder is made of plastic or something really light, so it has a very low mass, so it has a low starting threshold and very quick response, and for the most part these systems are low maintenance. This was the standard on the Belfort 2000 that was used by the ASOS as the standard anemometer up until 2005. So those are the characteristics and the transducers of cup anemometers. Next time, in the next video, we'll discuss propeller anemometers.